Let's continue our discussion on guidelines for asymptotic analysis. Here we will discuss about the if-then-else statements. How much time a particular program will take when we have if-then-else statements. Let's say we have this program which consists of if-then-else construct, and we are asking here the input from the user, and then we will check this condition. Is n equals to 0? If that's the case, then we will evaluate this statement, else we will go in within this else construct and will evaluate this statement n number of times, right? The worst case running time in the case of if-then-else construct is evaluate the running time of the test part, that is this part, then add it with the running times of the if part or else part, whichever is larger, not both the parts, let me tell you. Because at a time we are either executing the if part or else part. Whichever is taking the larger time, we will add this to the test part. This is how we will calculate the running time of the if-then-else construct. This is as simple as that. For if part, obviously this condition checking will take just constant amount of time, and the statement within this if construct will also take constant time. That's my assumption, of course. You should assume that the statement, when I am writing this in the comment section, then it will always take constant time. That is the assumption, okay? Then the total time in this case will be 1 plus 1, which is equals to big O of 1. Doesn't matter, this is 1 plus 1, which is again a constant, right? So the worst case time complexity will be constant, that is big O of 1. So it is a constant growth. This if construct will take constant amount of time. Now let's evaluate the else part. Here in this case, in the else part also, we need to evaluate the running time of this particular statement. That is this condition checking, right? N equals to 0. This will take constant time, right? Because it doesn't matter whether we will evaluate the if part or else part, we always have to check this condition. In order to get into the else part, you have to check this condition. So this must be calculated in the case of else part as well. So the running time for this statement must be calculated in the case of else part as well. Apart from this, you can see that within this else part, we have this for loop which runs from I equal to 1 to n. And within this for loop, we have the statement. So this statement will get evaluated n times. So it is clear that this statement is executed n times. So the total time will be 1 plus n, which is equals to big O of n, right? So what is the overall time complexity? It is big O of n, because this else part is taking the larger amount of time. Test part plus the else part will give us this time complexity, that is big O of n. Now the next guideline, that is about logarithmic complexity. What is logarithm, by the way? Let's take this example and try to understand what is the meaning of logarithm. What does this statement says? The above logarithm says that how many times 2 has been multiplied by itself. I'm talking about this 2. How many times 2 has been multiplied by itself in order to obtain value 8. 2 has been multiplied 3 times, right? 2 into 2 into 2 is 8. So 2 has been multiplied 3 times. That is why log 8 base 2 is 3. So this is the meaning of logarithm. It always gives how many times a particular base has been multiplied by itself in order to obtain the value under consideration. So answer is 3. Logarithmic time complexity is achieved when the problem size is cut down by a fraction. Let me tell you that logarithmic time complexity is lesser than the linear time complexity. It is achieved when the problem size under consideration is cut down by a fraction. How is that so? Let's see the example over here. Here you can see this for loop runs from 1 to n, and we are evaluating this statement. You think of this that this for loop will run n time, but here's the catch. Here I is not incremented by 1, but I is multiplied by 2 every time. So here in this case, obviously this is not a normal growth, right? This is not the case that this will run from I equals to 1 to n, total n times. No, it is not the case. Here I is not incremented by 1. It is not a step size increment. I is multiplied by 2 every time. How to evaluate the time complexity in this case? In the iteration number 1, initially I is equal to 1, right? So initially I is equal to 1. So this is equal to 2 to the power 0. Can we say that 1 is equal to 2 to the power 0? This gives 1. I'm writing this in this form, okay? In the iteration number 2, I will be 2. We can write this 2 in the form 2 to the power 1. Isn't that so? Now in the iteration number 3, I will be 4, not 3, right? Because I is multiplied by 2. Here previously the value of I is 2. 2 is multiplied by 2, which gives 4. We can write this as 2 to the power 2. Similarly for iteration number 4 and iteration number 5, here in this case we are getting I equals to 8 and I equals to 16. We can write this in this form 2 to the power 3, 2 to the power 4. Let's say we go up to iteration number k. Then in that case this will be 2 to the power k minus 1, because you can see over here that for iteration number 1 this is 2 to the power 0. Iteration number 2, this is 2 to the power 1. It is always 1 less than the iteration. So here in this case, if we are going up to iteration number k, then this will be 2 to the power k minus 1. And this is equal to n, because the last value over here is n. when I is equal to n, this is what we are getting. This is 2 to the power k minus 1. This is the last iteration. So we know that n is equals to 2 to the power k minus 1 at the end. Now we need to calculate how many iterations are there. How many times the statement under for loop has been evaluated. For this purpose, we will apply log on both sides. When we apply log on both sides, this will be log n base 2. This will be log 2 to the power k minus 1 base 2. This gives k minus 1 only, and this will be log n base 2. So k minus 1 is equals to log n base 2, which gives k equal to log n base 2 plus 1. So the time complexity is obviously big O of log n base 2. Obviously we are eliminating this constant term, it doesn't matter. So here the time complexity will be log n base 2, isn't that so? Let's consider one example to understand this properly. Initially I is equals to 1 and this loop runs up to 32. But let me tell you that we are incrementing not by step size. We are multiplying I by 2 every time. So again, we know that how many iterations this particular for loop will run for. We need to calculate the number of iterations so that we could get that how many times this hello will get printed on the screen. Or we can calculate the time complexity, that how many times this statement has been evaluated. So this is given by k, and we know that k is equals to log n base 2 plus 1. Here we know that n is equals to 32, right? So let's replace this n by 32 over here. This gives log 32 base 2 plus 1. Log 32 base 2 is 5 and 5 plus 1 is 6. So number of iterations are 6 in total. So this means that hello is printed on the screen 6 times. So the time complexity is obviously log n base 2, right? Let's consider one more example here. Here in this case, we have reversed everything. Instead of I is equals to I into 2, we have I is equals to I divided by 2. Let me tell you that this will also take logarithm time. We are running this from I equals to n up to 1, just reversing the whole sequence. The time complexity will again be logarithm, okay? Let's see how. In the iteration number 1, I is equals to n divided by 2 to the power 0. In the iteration number 2, I will be n divided by 2 to the power 1. Why this is I equals to n divided by 2 to the power 0? Because we know that initially I is equals to n, we can write this in this form. Then I becomes n by 2, which means I is equals to n divided by 2 to the power 1. Then it will be n divided by 2 to the power 2. And so on, this will go up to n divided by 2 to the power k minus 1 for iteration number k. And this is equals to 1 because lastly we are getting this 1 value, right? This is not equal to n, this is equal to 1. So n divided by 2 to the power k minus 1, which is the last iteration, so it is equal to 1. N divided by 2 to the power k minus 1 is equal to 1, which means that 2 to the power k minus 1 is equal to n. This is similar to the previous case, isn't that so? Again, we will apply log on both sides. This will give us k minus 1 equals to log n base 2, and finally k is equal to log n base 2 plus 1, which is again big O of log n base 2. We haven't done anything, we have just reversed the whole sequence. Again we are getting this logarithm time complexity. So this is all about the guidelines related to asymptotic analysis, and now you are aware about how to calculate the time complexity in different scenarios. Okay friends, this is it for now. Thank you for watching this presentation.